Hello everyone. Today we're going to be talking about rational functions. Now a rational function is a function of the form y equals f of x divided by g of x, where both f and g are polynomials. So since you have a function in the denominator, you are going to have some x values here. And remember, since we're dividing, there is one value that our function cannot equal, our denominator cannot equal, and it is 0. Right? So when our denominator equals 0, our function is undefined. So where that denominator equals 0, where those values are 0, we have asymptotes, just like we do with exponential functions. So a rational function can have both horizontal, just like an exponential function, and vertical asymptotes. Okay? A rational function can have or has branches. It'll have one more branch than the number of vertical asymptotes it has. So if we look at this drawing on the right, the graph, here are two branches in blue, right? And then we have our asymptotes as dashed lines in red. So here's our vertical asymptote, and here is our horizontal. So again, both of these are found from our function, and our vertical asymptotes are found from our denominator when our denominator equals 0. Okay, so we'll also talk about holes in a few moments, and we'll talk about how to find the horizontal asymptotes as well. So let's look at this table here that kind of organizes our information so that we can find what our asymptotes are. And remember, asymptotes are lines, so they have equations. So vertical asymptotes have the equation x equals some number, and horizontal asymptotes have the equation y equals some number. We'll talk about slant asymptotes a little bit later, but now let's focus first on our vertical asymptotes. Now, very important to find both types of asymptotes, you want to make sure to factor both of your polynomials, both the numerator and denominator. And so I just abbreviated numerator as NUM and denominator as denom. Okay? So once you factor both the numerator and denominator, to find the vertical asymptotes, you want to set the denominator equal to 0. So when you set the denominator equal to 0, you will get the x values that make your denominator equal to 0. Your vertical asymptotes are at the x values that are in the denominator, but not the numerator. So let's look at a little example so that we can see this. So say I factored my equation here and I got x minus 3 over x minus 3 and x plus 3. So we can see here that x minus 3 is in both the numerator and denominator. So what would actually happen with those is they would cancel, and we wouldn't have a vertical asymptote at x is positive 3. Instead, since x plus 3 is left over in the denominator, we would have a vertical asymptote at x equals negative 3. So I got that negative 3 by, remember, setting this equal to 0. So x plus 3 equals 0, and solving for x to get x equals negative 3. So that's what we mean by setting the denominator equal to 0. Okay? And we'll practice this more in class, but our graph is going to look something like this whenever we have a vertical asymptote. So we have our vertical asymptote, and then our function is going to get very, very close to it, but not quite touch it. So this is just a small sketch of what our graph could look like. So now let's talk about horizontal asymptotes. Now there's 3 different instances where we could have a horizontal asymptote. And all of these cases are determined by the degree of your numerator and degree of your denominator. So let's let n stand for the degree of the numerator, And let's let D stand for the degree of the denominator. So let's look at our first case. If the degree of the numerator is bigger than the degree of the denominator, then we have no horizontal asymptote. Okay, so I'm going to go to the next page to show you an example of this. So if the numerator has a larger degree than the denominator, then there's no horizontal asymptote. So we could have an example of a function like this, so negative 3x cubed plus x minus 1 all over x minus 2. So we can see here that the degree of the numerator is 3 and the degree of the denominator is 1. So because 3 is bigger than 1, there is no horizontal asymptote. Okay, so that's one of the cases. Let's look at the next case. The next case is when the degree equals the denominator, so the numerator equals the denominator. Our asymptote can be found by dividing the coefficients of the terms of the highest degrees. So our asymptote is at the line y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. Okay, so let's look at an example of that. So here we can see our function is f of x equals 4x squared plus 1 over x squared minus 7. And in this instance, we can see that both the numerator and denominator have a degree of 2. So what we're going to do is, since these two are equal, 2 equals 2, we're going to take our leading coefficients. Our leading coefficient of our numerator is 4, and our denominator is actually 1. And what we're going to do is we're going to divide them. So that means that our horizontal asymptote is at the line y equals 4. Okay, so let's look at our last case. Our last case is when our numerator is smaller than our denominator. And when that happens, our asymptote is at the line y equals 0. So let's look at an example of that. So, for our example here, we have the function 2x plus 2 over x squared minus 3. As we can see, the the degree of the numerator is 1 and the degree of the denominator is 2. So because 1 is smaller than 2, that means our horizontal asymptote is at the line y equals 0. And it will always be at the line y equals 0, so the x-axis, when the numerator is smaller than the denominator. So let's go back to the table so we can draw an example here. So here is a possible example, just what the graph would look like. You have a horizontal asymptote here, and you could have however many branches you have around it. One part of the branch will just get very close to that horizontal asymptote but not actually touch it. Okay. We will talk about slant asymptotes a little bit later, but I want to specifically talk about holes where our function is undefined and intercepts as well, x-intercepts. Let's first talk about x-intercepts. X-intercepts are kind of nice because we already know how to find the x-intercepts of a function. What we would do is we would take our factored numerator and set it equal to 0. Wherever those factors equal 0, whatever x values, those are our x-intercepts, just like if we were factoring a quadratic equation. Right, so x-intercepts are the only things that we find from the numerator. Holes are from the denominator. So we already saw an instance of a hole when we were looking at vertical asymptotes. So to find holes, we would still set our denominator equal to 0 after we factor it. And a hole is the x value that is in both the numerator and denominator. So if we were to look at an example, we could actually look at the example we had before in the vertical asymptotes. Since that factor x minus 3 was in both the numerator and denominator, that is actually where a hole is at. A hole, for that example, is at the point with our x value at positive 3. And to get our y value, we would just plug that into our function. Okay, so when you are graphing and you end up having a hole, when you graph it, you would just come up to that point, whatever 3 comma whatever value it is, and you would actually just draw an open circle, and then you would continue on your function as you went. Right? So we're going to practice all of this next time in class, maybe not tomorrow, but next time in class. So I will see you then.